Good afternoon, everybody. Welcome. Class number 4. So today we will wrap up chapter 2, the math review from our book. I was originally planning to go a little faster, but I realized that was a little bit too ambitious. So sticking to my original schedule. So far so good. I hope you see that on Canvas and also in messaging through Canvas. I posted the chapter schedule, so it should be quite clear now, at what pace we're going to be going. I haven't picked the final set of homework problems yet, but I will do so soon. It should be by the end of this week. Absolutely, it should be there. And then, like I said before, the homework will be problems that are example exercises from throughout the text. So hopefully when you're studying ahead, you're reading the text ahead, you will already be doing these exercises, and if not doing them, you should at least think about the strategy. That brings me to something that is that's quite important, and I hope that you all do this. When you study or when you read material, there's a lot of evidence that says that you'll remember and understand it better if you do some scaffolding in advance. So in other words, even before you start reading the chapter, just look at the titles of the sections and look and see, okay, what are we going to be talking about? What subjects are we going to be talking about? And then just kind of like browse through the pages, see what kind of symbols show up. If you want to go all out, write some questions on a piece of paper that you think, oh, by the end of this section, I'll probably have an answer to how this works, or we'll have discussed these things. And then when you're starting to read it, you'll be able to actually put the whole thing in context much better, and it's going to help you understand the material a lot better. And specifically with material that goes pretty fast and is heavily mathematical, it's very easy to lose track of where we are. So if you do this in advance, that's highly recommended. I used to do the following as an undergrad. I would literally take a piece of paper and I would put it on my textbook and go line by line. I would scribble along on a piece of paper and I would try to predict what would be coming next. And that's really, really helpful, because if you just kind of read, or if you're just looking at my lecture, hopefully during the lecture you will think, well, of course that makes sense, because I'm trying to explain it in a manner that actually makes sense. But if you have not actually confronted your brain with the fact that what I'm going to be talking about is probably new to you, you will not actually learn the material. You'll just kind of accept it at face value, but your brain will not necessarily accept that as new knowledge. So the only way to do that is to confront yourself with the fact that you might need new knowledge, and the only way to do that is to try to work ahead. So highly recommended that you try to do that, because then you'll get by much faster. Okay, so today let's continue talking about rotations. So so we did start on our rotations in our previous class. So in 2D, if we have a coordinate system, let's say we have some x and some y, and we have some kind of a vector, some vector a, then if we do a rotation, we can basically take that vector, and we can either rotate the vector or we can rotate the coordinate system. Those are obviously complementary exercises, but this is one of those where we rotate the vector. Then if we're taking that rotation, and then we're getting this expression. So it's the same expression as we were analyzing before, but now it is in matrix form. So the first thing I want to talk about is the linear algebra of this problem, because I think it's something that probably we could use a little bit of refresher in. So what do we mean? Rather, what do I mean by the linear algebra of the problem? So if this is our matrix, let's call that our matrix R, then that matrix has it's a 2 by 2 matrix, and it transforms vectors that are 2 by 1 into vectors in some other coordinate system that is also 2 by 1. And there are some normal things that we usually ask, and it's almost Pavlovian when you start studying these kind of things. You see a matrix. I certainly am have that response. Is well, what are the eigenvalues and eigenvectors that are corresponding to this equation? So what do we mean by eigenvalues and eigenvectors? So let's say we have some vector R, and so we're gonna take our a vector, and I'm writing it as a vector, okay? And then we're gonna take our matrix R, and then we're gonna multiply that by some other vector. And now the question is, are there rotations, or in other words, are there values for A for which if we let this rotation operator work on that vector A, that we get the exact same vector out, except it might be rescaled. So that's a common eigenvalue problem. So for instance, if you have some kind of a matrix A, and then the eigenvalue equation that you usually solve is this, and then so this would be your eigenvalue, and this is your eigenvector. Okay, now we should be a little bit careful, right? Because this rotation is a rotation that is still a function of theta. So if we're going to look at eigenvalues and eigenvectors, we need to decide what theta we're talking about, and that's what makes this analysis a little bit trickier. So so let's first try to anticipate what's going to happen. So let's say we have some kind of a version of this rotation, and we have a vector, and let's say the vector is flipped over to the other side. Then that vector is inverted, right? So that means that there's an eigenvalue -1, and that vector is whatever that vector is. Now, if we have this rotation, then for a rotation of theta is equal to 0, you see that cosine theta is 1, cosine theta is 1, sine theta is 1, sine theta, sorry, 0 and 0, right? So if theta is 0, then we're not actually rotating. Then this is actually the identity matrix, which means that any kind of vector that we put in, we're going to get out again, right? So in other words, that should give you an eigenvalue of 1, and the corresponding eigenvectors will be basically the entire xy plane. So we'll actually get 2 vectors, or in other words, we'll get a single eigenvalue 1, but it's doubly degenerate. Now, if theta instead, if it is, let's say, pi, then this is -1, this is -1, that's 0, and that's 0. And now that means that any kind of vector that we put in here, ax, ay, is going to be inverted. So -ax, -ay. So that means that the eigenvalue is -1. And therefore, also the eigenspace that corresponds with it is, again, the entire xy plane, right? Because anything in that xy plane completely flips all the coordinates. So, so having said that, I'm going to have you actually solve the eigenvalue problem, and we'll do that in Nearpod. So find the real eigenvalues and vectors of R. So let's walk through this. Remember what I was saying is that R is a function of theta. So really what you're supposed to do is, for any kind of value of theta, you need to determine whether this this matrix has eigenvalues, and then afterwards whether they're real or not. So if you start off like this, solving this basic, following the basic recipe of finding what the eigenvalues and eigenvectors are, you have to keep that in the back of your head, that what we're actually doing is we're still allowing theta to be a continuous variable, and we haven't actually pinned it down yet. So we are simultaneously solving the eigenvalue problem for an infinite set of R matrices, right? Because they can all be different by infinitesimal angles, angle amounts d theta. So, but if you ignore that, then what you're doing is you'll just write your cosine theta minus lambda sinus theta sine theta cosine theta. Okay, you expand that. You get this quadratic equation. You use your square formula, and you get cosine theta plus or minus I sine theta. So that's equal to e to the power plus or minus I theta. Okay, now again, these are the eigenvalues of this matrix when you let theta be any value. I asked for the those versions of R that have real eigenvalues, and then obviously the only ones that are possible are where you pick theta is equal to 0, right? So theta is 0, then your cosine theta is 0. This is 1. Your I sine theta is 0. Done. So cosine theta is 0 gives you your lambda is 1, and then your theta is pi gives you your lambda is minus 1. Okay, so then you want to find the eigenspace or eigenvectors. So if cosine theta is 1 and lambda is also cosine theta, then obviously this is 0. This one's 0 because your theta is 0, so that's 0, that's 0. So you're trying to solve this problem, and that's actually valid for any kind of linear combination of A and B. So in other words, the eigenspace or the set of eigenvectors, you could actually pick any kind of eigenvectors, but it's spanned by two orthogonal vectors. So it's 1, 0 and 0, 1. And if you were particularly masochistic, you could also write the span of 1, 1 and 1 minus 1. That's fine too. But why would you do that to yourself? Okay. Okay, let me make sure I make this point. So you factor out your 4, so you get a 2 here, and then you use the identity that cosine squared theta plus sine squared theta is 1. So therefore, cosine squared theta minus 1 is minus sine squared theta. And then you have the square root of minus sine squared theta, which means sine theta times I. Okay, so let's see what happens when we take theta is pi. Well, then we get lambda is minus 1. Now, of course, that means that again we're going to get cosine theta minus cosine theta. I mean, theta might be different, but that we're still going to get a cosine theta minus a cosine theta. So again, we're going to get a 0. Again, we're going to get a 0. Again, we're going to get a 0, and again, we're going to get a 0. So that means that the eigenspace is again, because it's the same matrix, again, just R2. Oops. R2. All right. Now, what does that mean? Well, that means, like I was saying in the beginning, that any kind of vector, if you don't rotate it, so theta is 0, then any kind of vector will keep both the x and the y components the same, which means the vector could be the entire xy plane, which means that the eigenspace corresponding to that lambda is 1 is just the complete xy plane. Theta is pi, that means we're going to invert everything. If you let that work, you're basically inverting your x and your y coordinates. So any kind of vector in the xy plane is a solution to that. All right. So now that we know that we're going to get these, we can say some abstract things about this matrix as well. we can we know what the determinant of this matrix is going to be. It's going to be a function of theta, right? But I hope that you remember from your linear algebra that the determinant of R is going to be the product of the eigenvalues. Okay, so so for instance, if we say the determinant for R where theta is 0, we hadn't lambda as 1, but actually it was doubly degenerate because the and I kind of skipped over that, so let me make sure that I make that point first. Let me do that first. So note, if theta is 0, then your characteristic polynomial is lambda squared minus 2 lambda plus 1 is equal to 0. Did I do that right? Yes. So that means that's lambda minus 1 squared is equal to 0. So that's lambda is 1 and it's doubly degenerate, right? So second order polynomial, 1 is doubly degenerate. So the product of lambda 1 times lambda 2 is lambda 1 times lambda 2 is 1. All right. Now, if you have theta is pi, then we're going to get our characteristic polynomial. Here we go. Lambda squared plus 2 lambda plus 1 is equal to 0. So that means lambda plus 1 squared is 0. So that means lambda is 1, but it's doubly degenerate. So again, lambda 1 times lambda 2 is 1. All right. Now, if we don't assume a specific value of theta, then we actually have two eigenvalues. We have one. We have a lambda plus, which is e to the power I theta, and we have a lambda minus, is e to the power minus I theta, and the product is 1, even if the thetas aren't giving you eigenvalues that are actually not real. Now, I don't quite know what to do with a rotation matrix when the eigenvalue is not real, because that means that all of a sudden we have no longer R2, but we've expanded R2 with an imaginary axis, and we didn't actually put that in the problem. So I don't want to get in there, but I think it's interesting to see that even if we allow for that, the product of those two eigenvalues would still be 1. So either way, our determinant of R, independent of theta, is always going to be 1. Okay, short detour. Let's say you have some kind of a matrix A, then you can always write that in the following way: C. So C1 D C, where D is a diagonal matrix. That's, by the way, that's not always true. There, I forgot exactly what the set of limiting circumstances are, but this is a diagonal matrix, which means that on the diagonal it's going to have lambda 1, lambda 2, lambda 3, et cetera, et cetera, et cetera. Okay. Now, if you have a if you now want to raise a to the power n, so for instance, you're studying the Fibonacci sequence, you can basically write that as a to the power n is c minus 1 times d times c times c minus 1 times d times c times et cetera. So every time you're going to get these two that are going to be out, I might be reversing my c and my d, and you'll find that it's c minus 1 d to the power n c. And the determinant of the inverse is always 1 over the determinant of the other. So the determinant of this is going to be determinant of this, and therefore it's going to be the product of the eigenvalues raised all by that power. So knowing those things and knowing these kind of transformations are super useful. This is if you want to study the Fibonacci sequence, by the way. this is how you can find a single closed expression for the population P after n and P after n minus 1 cycles. It's some kind of a closed expression. So you don't actually have to do the Fibonacci sequence. You can just write down one expression, and that's how you find it. Anyway, linear algebra is cool. So after this, now let's talk about matrix, a little bit more about the matrix notation in a little bit more for rotations in a little bit more abstract sense. So for instance, if we have a complete set of axes, so EI, and let's say it's is a complete set of coordinate systems, set of basis vectors. That's what I was looking for, basis vectors. Complete meaning that if you span and you add all of your eyes, so for instance, if you're doing this in R3, then you've got 3. And if you take any kind of linear combination of E1 through 3, you can find any spot in R3 as some kind of a sum of these. So it's complete. It's also orthogonal, and it's also normal. So what do I mean by that? Well, it means that EI dotted with EJ is going to be delta IJ, right? So these are unit vectors. So sometimes this book doesn't do this, but I would usually write my unit vectors like this with a little hat over it. I'm not sure why we don't do that. Okay, so if that's the case, then we can figure out what vectors are in this coordinate system by just taking doing a decomposition. So for instance, we can say we have some kind of a vector A, and we can write it in its components, A, E, I, or we can write AI as the projection of A on EI. So you can go both ways, right? And that's only because it's a complete set, and it's they're all normal vectors. Otherwise, you wouldn't be able to go back and forth. Okay. Now let's see what happens if we are rotating our coordinate system. So let's say we have some kind of a so we're rotating the coordinate system, by the way, not the vector. Those are each other's inverse. So let's say we have some kind of a rotation operator. So rotation operator, and it's an operator, and it's got a normal and it's got a theta, and we're using some kind of a right-hand notation. So put your thumb on the vector n pointing up, and then your fingers indicate positive theta, right? So this is your rotation around your n hat by an angle theta. Okay, so that's our rotation operator. Then we can actually, because it's a complete set of basis vectors, it spans whatever r of n that we have. I know I'm using r twice or now, so we have the r operator, and we also have r as the space. But okay, let's sweep that aside. If we let this operate on the basis vector, so for instance, we could say, okay, we're going to take REI in after applying this rotation, so n hat theta is what happens with REI, right? So so this rotation moved this basis vector to this different basis vector. In that case, we can write our rotation in a general sense, or rotation matrix in a general sense like this. So we can just say we're going to take our rotation, and instead of oops, I'm sorry. we can actually write that like this. So this is still our rotation operation. Now, this rotation operation was applied and gave us this one. So therefore, the input to that was an unrotated vector. And now we have a matrix, and that is just the rotation matrix. That is Rij. Okay, so that's a little bit. So this is an operator, rotation operator, and this is our rotation matrix. Okay. Now, if we do that, let's see what happens to a vector. So let's say we have a vector A, and we would like to know what happens with A if we, instead of expressing it in EI, we express it in the rotated coordinate system. So let's say A in the rotated coordinate system would still be AI with a prime, but now we would have to sum over the primed basis vectors. So this is the rotated basis. And this is the original basis. Meanwhile, back at the point. So let's say we have we have the same vector A, but now instead of expressing it in our coordinate system, where was I? E of I, we're doing this in the rotated coordinate system, E of I prime. Some people would put primes here, right? Then that means that A of I prime is basically that vector A dotted with the E of I prime. Now, we would like to know how the A of I is related to the original coordinates. So let's see what happens. So we know how we can get EI prime from the original because we just get it by rotating. So we just do do a rotation dotted with the rotation and theta acting on our EI, our original vector, right? So I just take this expression for this. Now our A vector is still in the EI basis is AI, but we have to be careful now because we cannot reuse this AI. We have to use J and then EJ dotted with the rotation operator acting on our theta. Okay, so I haven't really done anything. I just decomposed A in terms of the original unrotated basis. But what we now have here is the original one, right? So that is still recognizable as our AJ, but now this is a matrix. Where is my matrix? Here we go. So you see EI dotted with a rotation of EJ is the matrix Rij. Now, let me, to not further confuse you, let me just swap these so I don't mix my mix my indices. Okay, so this is, let's call it the original. And this I, and let's call this J. And now this part, you should recognize, is the same as this part. So that means we have an A, I, R, I, J. So now we have written our rotation in indicial notation. So AI prime is the AI multiplied with R, I, J. Yeah, it's when you start rejiggling indices. So sorry about that. For posterity's sake, I had my indices when I changed them here. I should have also gone back and changed them here. But now we're good. Now we have the coefficients of the vector A in the rotated coordinate system. That's why they're indicated by prime. Is a set of 3 numbers, J, where we let J run through 1, 2, 3. And we get that by doing a matrix product of AI with an Rij, where AI is the original coefficients of the same vector, right? But we rotate the coordinate system. Now, look very carefully at this. This is usually not how we do matrix multiplication. I had my matrix multiplication here somewhere. Oops. Usually we write matrix multiplication like this. We have some U of I, and in the matrix coefficients, the first one is indicating the row, and the second one is indicating the column. So if you put a vector on the right and you multiply that over here, you get this product. So this does not look exactly like a matrix multiplication, okay? But you know, there's a summation convention, so it should not be hard to read, because this is actually rather explicit. Now, back to the question that we were asking at the end of the previous class. We had for a very explicit rotation, you know, the rotation in 2D, where we said we had the rotation matrix. We said, okay, what is the length of AJ of A in the rotated coordinate system versus the length in the rotated coordinate system versus the length in the original coordinate system, and it should be the same. So now we're going to actually put that statement to use. So so what does that mean? Well, let's say we want to know what this is. Okay, so that's the product of AJ in the rotated coordinate system. Okay, now that is going to be, now I need to be really careful. It's going to be, I'm going to put it in parentheses. It's going to be the original AI with an RIJ and another AK, because it's not the same, KJ. Okay, so that's all I did. So, and I wrote this. Like I said before. So this A of J you get by doing this sort of matrix multiplication where you sum over dummy index. And this dummy index cannot be the same for this vector as it can be for that vector, because that's AJ on the left and that's AJ on the right. So these are 2 different matrix multiplications. And that's why you need to make sure that you actually have them as 2 different matrices. Okay, so so now let's reorder this a little bit. So we have an AI, and now we have an RIJ, RKJ, and now an AK. Okay, now we would like for this to be equal to the original length. So that means that at some point, this needs to become AI again. All right, so this is what we want. Okay, it's not necessarily given yet. We have verified it for a very specific matrix. Okay, what does that mean? Well, that means that this product needs to give you an A of I. So Rij, Rkj, AK needs to give you an A of I. Well, look at what we're doing here. So this is actually, it's a sum over J. We have also a sum over K, and the only free index here is I. So we can write this as something that is summed over, J. This is actually, if you take this product, there's an I and a K, and there's a sum over J. So you can replace this with a single, let's call it a matrix, with a single matrix with two elements that after, so something with two elements, and let's call that Ik, that after we multiply that with our AK, we get AI. Okay, now what matrix could we use that would basically swap out our K for an I? Well, that will be the identity matrix, our Kronecker delta symbol. Okay, so that means, therefore, that delta Ij, let me actually keep using the same symbol. Delta Ik is Rij, Rkj. All right, now this is important. If you look very carefully, you see that this is a matrix, a little bit like a matrix multiplication, except we're multiplying by summing over the second element here and the second element there. Now, if you have let's say a regular, whatever that means, matrix product. So that, for instance, we have a matrix A, and we're going to do a matrix product B, J, K. We are summing over this one and this one, right? Because remember, you're doing a matrix product. So the index of this thing is reversed. So actually, this is the transpose of this. So actually, what this says in matrix notation is R transposed R. And what this says, this is the identity matrix 1. Now, we know that there is only one matrix that if we multiply it by it, we get the identity matrix, and that is the inverse of that matrix. So actually, the inverse of R is the transpose. Now, finally, you should know that for any kind of any kind of matrix, the determinant of the transpose is the same as the determinant of the original. So therefore, the determinant of the R transpose is 1, because the determinant of the identity matrix is 1. So that is the determinant of R squared. So therefore, the determinant of R can be plus or minus 1. Oops. Plus or minus 1. And after the break, I will walk you through why we only like this to be positive. Why are we using the one with positive only? First of all, the one that is negative is usually what we call an improper rotation. It is actually an inversion, not really a rotation. But think about what a rotation is. So a rotation means that there is, in 2D, there is a rotation where we can either keep all the vectors the same in that plane, or we can flip both the x and the y components in that plane. Okay, so so that means you either have a doubly degenerate eigenvalue of 1, or you have a doubly degenerate eigenvalue of -1. Okay, but that is a rotation around the origin. Now, if you do a rotation around some kind of a vector, n vector, right? So n vector, there is still a rotation around that vector, which means that in the plane perpendicular to that vector, it is still a two-dimensional rotation problem. So that eigenvalue problem is the same. It's just that plane might be tilted. So even though n vector might be pointing in a stupid way, like this, that plane might have a really ugly expression, but the rotation in that plane is still the same rotation we studied before, which will have either a doubly degenerate eigenvalue of 1 or a doubly degenerate eigenvalue of -1. Now the question is, what's happening with the stuff that is perpendicular to that plane? Well, that's the stuff that is pointing in the same direction as n. Now, when you rotate, vectors with a component in the n direction are not going to change the n component, right? Because you're rotating around n. So the eigenvalue corresponding with vectors that are parallel to n is 1. So you have a doubly degenerate -1, product being 1, times whatever eigenvalue corresponds to stuff that's parallel to the normal, which is 1. So you'll get a product of 1 and 1 and 1, or 1 and -1 and -1. Either one, you'll get 1. So what we were doing was rotating components of a vector A of k, but we could also be rotating components of more interesting things. So for instance, the book has an example where, for instance, you could do, this is Ohm's law in differential form. If sigma, which is the conductivity, if that's a scalar, then your material's isotropic, right? So the conductivity is the same in all directions. But it doesn't need to be isotropic. So for instance, graphite. Graphite has an in-plane conductivity that is about 1,000 times higher than the out-of-plane conductivity. So the direction of J and the direction of E matter. So for instance, you could say, well, J actually has components I, and sigma actually has components, and let's call it ik, and we're adding over k. So now we're doing a vector matrix vector product. And now this is what we call a tensor of rank 2 because it's got 2 inches. This is a tensor of rank 1. That's a tensor of rank 1 as well. And now these ones, the conductivity tensor, we could write it as, let's say, sigma ik. We could write this as some kind of a I and a bk. And this tensor of rank 1 would transform just like this rotation that we were doing before. And this tensor of rank 1 would also rotate in the same manner. So you can describe the rotation of this tensor of rank 2 by just, instead of having a single multiplication with a single rotation matrix or tensor R, anytime you have one more index, you need to do a rotation not only for the stuff that's going in the I direction, but a rotation for stuff that's going in the X in the K direction. So we'll get to that stuff later, but just remember that if we go from 1 to 2 to 3 to 4 at some point, for every index that we add, we need to add another rotation. Arbitrary, curvilinear, coordinate systems. Okay, now I'm going to put arbitrary in parentheses because we'll only use curvilinear coordinate systems that are actually locally orthogonal. there's no particular reason why you could not have a skewed coordinate system, so you get really weird cross terms, but it just makes life a little bit more complicated. We don't necessarily need those kind of coordinate systems in our in our problem space. So let's say I'm gonna draw. Let me actually use some arbitrary. So let's say we, and then these are my two. I'm supposed to draw these orthogonal. I was just making a point that it's supposed to be orthogonal locally. So let me actually make it orthogonal. Okay, so here we go. So orthogonal and orthogonal, something like that. Yeah, so anytime these two coordinates axes cross, they are orthogonal. Okay, so let's call this u1 is constant, and let's call this u2 being constant. Okay. Now we can ask ourselves, how do we measure distances in this coordinate system? So let's say we have some kind of a vector A. How do we measure the length of A? Now that is actually made a little bit more complicated by the fact that if A is actually not, let's say, not an electric field, but let's say it's a position vector that actually goes from this point to that point, so it's actually bilinear, then actually the coordinate system is different in the beginning from the end point. So makes it very hard to talk about A as a vector if we have it really go macroscopic distances in a curvilinear coordinate system. So we usually don't do that. So usually what we'll say is, well, let's talk about infinitesimal vectors, dA vector, and then we can ask ourselves, how does that relate to our underlying coordinate system? So actually, let me use S because that's what the book does. Okay, and we can ask ourselves, okay, what is ds squared, so the length of this vector in this arbitrary coordinate system? Well, for small vectors, we could approximate this. We could say, well, if u1 is constant, then this is basically the du2 component of that ds vector, and we can call this the du1 component of that vector, and then together they form our ds vector. So then we can just do a simple Taylor expansion, because we're doing this for infinitesimal line segments ds, and then our it would be d ds d u1 times du1 squared plus ds du2 du2 squared. So it's just the Pythagorean theorem for a curvilinear coordinate system, right? So this ds du1, we can call that h1, and we can call this h2, or if we want to generalize this, we can actually write this as ds squared is the h1 sorry, hi di, come on, Henk, dui squared. So now we're summing over we're summing over all of these. And the HI are just our DS, D, UI. Okay, now, so if that's the case, then we know that we can write our ds squared as a sum of HI DUI squared. And now the question is just what are the h of i's? So for instance, in if we are working in Cartesian coordinate systems, our HI is just H1 is 1. Sorry, let me write this. X is H, Y is H, Z is 1. So then we get the regular expression. We just get ds squared is dx squared plus dy squared plus dz squared, right? So in Cartesian system, we get that. In our in another coordinate system, so spherical, our h of r is 1. Our h of theta is r, and our h of phi is r sine theta. So therefore, our generalized ds squared is just dr squared plus r squared d phi squared plus, I think I'm mixing my phi and theta. Hang on a second, let me make sure that I do this. Oh, yeah, exactly. I was mixing my phi and theta. So this is d theta squared, and this is r squared psi squared theta d phi squared. Now, if you have an arbitrary coordinate system, you should always be able to determine what these derivatives are. Basically how the position vector, because that's actually what S is, how the position vector changes if you change one of these arbitrary coordinates. And if you have an expression for that, then afterwards you can describe how you're going to measure length in that new coordinate system. In addition, you'll also in one go have expressions for the gradient of some function, the divergence of some vector field, the curl of a vector field, and the Laplacian, the Laplacian of a vector field. In terms of these, this triplet of values for h. So I'm not going to write these out because it's just needlessly complicated, but just as an example, just the gradient is going to be 1 over h I df dui, and that's the ith component of the gradient in this arbitrary curvilinear coordinate system, where h is this scale factor that basically makes everything show up as meters, and this is the partial derivative in the direction of that coordinate u on this arbitrary curvilinear coordinate system. And then if you want to know what the gradient is, you just add, write these. If you do this in R3, you have 3 of these expressions, and then you have your gradient. And there are similar expressions for these, but they become really long, and you can just look at the book for that. Well, ladies and gentlemen, is that's the end of today's class. We did it. We made it to the end of chapter 2. So that means we're finally off to the actual E&M using all of these tools. Somebody was asking, when are we going to see Fourier transforms? We will actually see it in the next chapter. So get ready. I hope you enjoyed this ride. I think it's really cool to start thinking about geometry in a little bit more general sense. I think there's a lot that you can learn about how to put problems together, because we're trying to write problems in a manner that doesn't really rely on a particular coordinate system, because otherwise we're not really talking about real physics. We're talking about just what happens to be true in a Cartesian coordinate system, and that those two are not necessarily related. So hope you appreciate the fact that we're doing this, and study up. And like I said, we will have office hours right after, and just hang around as long as you want. But at some point, if there's no more questions, I will terminate the Zoom session. Thank you, everybody.